What I want to do in this short screencast is to just go over some spectroscopy problems, give you an idea of what to expect. We've discussed plenty of kind of problems. You could be given a spectra and several structures and you have to pick the best fit. Alternatively, you could be given a structure and you have to predict the IR or NMR peaks where you expect those. The tables will be provided, of course. In addition, you could be given the spectra and the structure, and you have to predict what matches what. So I'm just going to go over a couple more problems just so you can see what to expect. If the question is, let's say, for a given molecule, what are the approximate chemical shifts? That is delta. So anytime I write down delta, that basically means chemical shifts. So we are talking about NMR. In case of IR, we have the wave numbers in centimeter inverse. So the question is that you have to predict the multiplicity and you have to predict the chemical shift of some of these structures. I have an H, there is a double bond O, there is a double bond O here as well, and, or rather, make that NH2. Make that NH2, double one here, double one here. What else? Yeah. And let's say you have to predict the number of signals and you have to predict in approximately what range these would appear. 1, 2, 3, there should be only one. Okay. So realize that there are 2 protons here and they are in the aromatic region, and these both are going to show up as doublet for each other. In addition, we have 2 hydrogens right next to a nitrogen, and we have 1 nitrogen connected to a hydrogen which is kind of like an amide hydrogen. So you're going to see the peaks for the aromatic ring. You're going to see those around 7, somewhere between 6.2 to 7, and the hydrogens that are connected, the protons that are connected to the nitrogen as well as the amide one, those probably will show up somewhere around somewhere between 3 to 4. One will be worth 2 hydrogens, the other will be worth 1 single hydrogen. Both of those peaks though will be broad. So these peaks right next to the nitrogen, these are supposed to be broad peaks or broader than what you see for the CHs. These CHs will be the aromatic doublets. Let's try another one. Perhaps so you have a T-butyl group and that's connected to a CH2 and an NH3 plus Cl negative, and you are supposed to predict where exactly these show up. Realize these are aliphatic hydrogens, so they're going to show up approximately 1 to 1.2 worth 9 protons, since it's a T-butyl group. There is no hydrogen here. You have 2 hydrogens which are right next to the nitrogen, so they're going to show up probably approximately around 3.5 to 4, since nitrogen is electronegative. And of course you have the NH3 plus, that's going to show up as a broad peak as well. Okay, let's take a look at another problem. I have been given the structure and 4 peaks are provided as well. No information on number of protons or multiplicity is given, and just on the basis of chemical shift, you're supposed to assign which peak is going to correspond to which kind of proton. So realize here that we have hydrogens on the benzene ring, so those are going to be my aromatic hydrogens. And as you know, aromatic hydrogens show up approximately around 7. So these peaks at 7, they will correspond to, let's perhaps number A and A prime. We have a 5.4, we have a 2.3, and then we have 1.5. 1.5 means it has to be something similar to an aliphatic chain. So hopefully you can realize that the three methyl groups that you have here, CH3s, they are away from the benzene ring, so they have somewhat of an aliphatic character. So the 9 protons here and the 9 protons on the other T-butyl, they're going to correspond to the 1.5, the peak at 1.5. So let's call that B and B prime. And now we are left with a C and a D. The peak at C, the methyl group that is connected directly to the benzene ring, and if you look up the table, toluene shows up. Toluene is basically CH3 connected to the benzene ring. That shows up at around 2.2 to 2.3. So this is going to correspond to the C proton, and the 5.4 is the OH. So that is the D proton, because that hydrogen is connected to a very highly electronegative element such as oxygen in this case. Okay, let's take a look at another one. You're given a structure and the question is to predict how many peaks would you expect in the proton NMR of the structure. Realize there is a methyl right here, and so that makes this molecule an asymmetric molecule. So you're going to see a methyl, let's call that A. This aldehyde is different than the other aldehyde. So this will be B, this will be C, and D. On the other side we have E, and the other aldehyde we have F. So total we should see 6 different signals in this particular case. On the other hand, if you had something like a CHO and a CHO, in this case, realize you can divide the molecule into 2 equal halves, and so in this case you're going to see only 2 signals. So just the presence of one methyl group just changes everything, and you go from 2 to 6 signals in this case. Let's do another one of these. What if you have maybe a 4-membered ring and one of the corners is an oxygen, and if you have to predict how many how many signals would you expect in a proton NMR? Realize that position A and position A prime is about the same, and there would be another signal for B. Now these among themselves can split, but that's beyond the scope of the course. They're called distereotopic, but you don't have to worry about that. Just realize chemical shift-wise that you're going to see 2 signals in this particular case. Let's try perhaps, since we are through the alkenes also, so we know a little bit about them. Let's say this is your structure and you have to predict the location of and the peak signal, how many of those kinds. You would say this is an A proton, that's B, C, D, and E. So total you will see 5 signals in this case. Realize if you had just cyclohexene, of course you could have divided the molecule into 2 equal halves, but not so much in the case where you have a C double bond O on one of the sides. All right, what about this question? The given information is that we have C4H4O as the molecular formula. The IR is given, the main peaks for that are provided, and then the NMR information is given, and the question is to determine the structure. So like I have said that empty number of times, you have to take a look at the index of unsaturation. So the starting point is the number of carbons. From that, subtract half the number of hydrogens. In this case, we have only oxygen. There are no chlorines, there are no halogens or nitrogen. So none of the remainder is going to contribute to this. And when you work on that, that comes out to be 4 minus 2 plus 1, which is 3. So this 3 could be present as 3 triple bonds. It could be present as, or I'm sorry, 3 double bonds, or it could be present as 1 triple and 1 double bond. It could be present as a ring and 2 double bonds. It could be present as a ring and a triple bond. So these are your possibilities. Now, I mean, the ring, I'm showing you a 3-member ring, but really, the reason I did that is because we have total of only 4 carbon atoms. So realize a couple things here. You cannot have, there's some things that you just can't fit in terms of the information that is given. You have only 4 carbons, and so that means that you cannot have this first scenario of having 3 triple bonds, because in order for you to have 3 triple bonds, you need to have at least like a carbon and then a single carbon and a double. So you need to have in this kind of a system at least 6 carbons, so that doesn't quite fit. You might be able to have the second scenario. You cannot have a triple bond and a ring. Even that is not feasible, and the reason for that is because each carbon is supposed to have essentially 4 bonds only, so this also is not feasible. So the options are that you could have perhaps 2 double bonds and a ring, and somehow we could fit that together. We also contain an OH, so let's see what are my possibilities. If I use a ring, then that means there should be 1 methyl to account for 1, 2, 3, 4 carbons, and perhaps one of these will contain a double bond O and a double bond like that. I'm just coming up with some structure just to kind of try to fit what fits a Lewis structure, really. But realize what's given in the IR. We do have a 1700, so that kind of fits the C double bond O. But then I have a 2200, and 2200 is reflective of a triple bond. 2850 is reflective of a CH3, and 3300 is reflective of an OH. So I really don't have anything at 1650, 1600 for the double bond, so this cannot be the correct structure, so that too is gone. So sounds like I have a system which contains a double bond and it contains a triple bond. So I'm going to try to write down a structure in a linear format and realize that the fact that I have a double bond in the system, which is not a C double bond C at 1650, but rather more like a C double bond O. Also, there is no 2700, so that tells you that it cannot be an aldehyde and perhaps is a ketone. Also, if it were an aldehyde, then the NMR should have shown you a peak at 9.0, and we don't have that. So that's not possible. So let's complete the structure for the Lewis structure and see if it fits what we have. I do have the C double bond O for the 1700. I do have the C triple bond C for the 2200. I have this methyl for the 2850, and I have the 3300 for the CH right next to triple bond. And I said earlier that you could say that 3300 is OH, but realize there is no broad written, so the options that I have which could be a triple bond CH or the OH. In case of OH, something should have been said about the broadness of the peak. And the other thing I would suggest is, since it's 1700, which is the carbonyl, and there is only one oxygen, so if carbonyl oxygen is already gone, you cannot have that alcohol peak there. And finally, the NMR. One of the peaks for NMR is worth 3 protons, so that's right here at 2.2, and the other one for the triple bond CH, that's going to show up at 1.8. So my NMR, my IR, as well as my molecular formula, all of that is satisfied. So my structure is this ketone that is given right here. Let's take a look at another one. So I have here 2 pentyne versus 1 pentyne, and you're asked to differentiate between the two structures, and you could be asked just general spectroscopically which technique would do this the best, and you have to explain that. Realize, since these are isomeric, you cannot use mass spec for this. You might be able to use IR or NMR for this. Let's take a look at IR. If you consider IR, the C triple bond C will show up a peak at 2100 to 2200 for the triple bond, and that will appear in both of them. So that's not the characteristic peak. Notice this is a terminal alkyne though, so you will see a peak at 3300, and that peak is simply missing in case of the 2 pentyne, so you won't see that. You are going to see free methyl in both of those at 2850. That free methyl will be existent. So what will help you identify for sure which one is 1 pentyne is the presence of that 3300 centimeter inverse. That is your key peak. If you were to do that using NMR, in case of NMR, realize you're going to see a peak around 1.8 to 2 for the CH3 and the CH2 and the CH3. However, in case of the other, I think I'm missing a CH2. In case of the second structure, which is the 1 pentyne, it will be corresponding to the 1.8, but only for 1 proton. So that will be the big difference between the two. Another example, maybe. Let's say you have to compare propanoic acid, and I went over this in class also, and you want to compare that to perhaps a free alcohol and an aldehyde, perhaps. How can you compare the two? Please realize this is a carboxylic acid, and so the OH for that starts around 2500 and is a really broad peak, goes all the way to about 3300 or so. It's an extremely broad peak. Whereas if it's an alcohol, it actually starts at 3300 and goes up to 3500. Again, it's a broad peak, but it starts at 3300 much later. And if it's an aldehyde, you will see a 2700 for the aldehydic proton, and of course the carbonyl should show up at 1705 or so. In this case, the carbonyl, because of the resonance, is going to be approximately around 1730, but I would imagine that the OH is going to be a giveaway in this particular case. Okay, let's do another one. I have here ethylamine, and I'm comparing that to acetamide. So the question is, let's say if you were to compare the C single bond N, and if you compare that to the carbon nitrogen single bond, which one of them is going to occur at a higher wave number, higher lambda bar? And hopefully you can see for the C single bond N, for the first one, it's just a primary amine, and if you compare that to the amide, in this case, you're going to see some resonance. So one of these is a pure single bond, the other has a partial pi character, partial pi character. And what that means is that it's going to have a greater amount of electron density between the carbon and nitrogen. So it's going to require a greater amount of energy to show the dipole. And so that kind of bond usually shows up more like 1600 or so, whereas the C single bond N shows at a much lower frequency, around approximately 1200 centimeter inverse or so. I think that will be all for spectroscopy for now. And I hope you go over these problems and the problems that we discussed in the wiki and prepare well for the test. I'll see you later.